Okay, so this is yet another tutorial on how to deal with more than one object acting on a system. In this case, we have what is called an atwood machine. An atwood machine, if I haven't already shown you in class, is we have two masses hanging over a pulley, and assuming they're unequal, the masses are going to accelerate. In this case, don't draw anything now. This is going to accelerate down, this is going to accelerate up, and we want to figure out what is the acceleration, and we could ask what is the tension on the string. Okay, so like anything else, we're going to figure this out by simply drawing an FBD and then working out the second law. The key is, like the other problems we saw before, is what did you choose as your system? Depending on what you're solving for, sometimes it makes sense to choose your system as one body or the other, or we're going to see it's choose them both to be your system. Okay, so a key thing that we want to understand here, as this pulley starts to rotate, both masses are going to move at once, and so the acceleration of A and the acceleration of B have to be the same. They're part of the same system, they're just separated by a string. Okay, so let's draw an FBD. We're going to be really careful about this FBD in the sense that we want to get the relative magnitudes of our forces correct. So based on this picture here, we can see A is bigger than B, so we're going to assume it's more massive. So I'm going to draw a relatively large gravity vector, and I'm going to call it MAG. Okay, I want to make sure I understand it's the mass of A times G, and we're going to make the B one relatively small. We'll call that MBG. Okay, now they're clearly connected by a string, and since they're connected by that string, there's going to be a tension in the string. Okay, so A is not free to fall. You might argue, well, because B is pulling up on it, and in a sense it is, but B is not directly in contact with A, so it's acting through the string. So we can understand that the downward force of gravity, I'm just drawing it, is kind of transmit through the string this way, so that the string ends up pulling mass A upwards. In other words, there's an upward tension on it, in a sense inhibiting its fall. So we can draw a tension vector on this, and we can call it TA. Now I'm going to make this TA bigger than this for reasons we'll talk about later, and smaller than this. So I'm going to call this TA. Okay, it's a tension on A because B is there. Now, by the third law of motion, if B is pulling on A, then A has to pull back on B with an equal and opposite force, and it's pulling on B via the string here, so we'll call that TB. And we'll put those there to indicate that they are equal to each other. So there is our force diagram. We're going to ignore any forces on the pulley, any friction, or etc. like that. So look at this force diagram and make sure you understand the nuances here. It's pretty straightforward that the two weight vectors aren't the same in the direction they are. What gets kids confused sometimes are the tension vectors. They have to be equal and opposite because they are action-reaction forces. And we'll see why this has to be smaller than this, and this has to be actually bigger than that. Okay, so to help us understand that, I'm going to just draw one other little thing here. I'm going to put a little acceleration vector, understanding this is going to accelerate up, and this is going to accelerate down. And that helps me decide for each one, which I'm going to call positive, which is negative. All right, so now we're going to write an equation for each. So I'm going to do mass A. I'm just focusing on these two forces. Those are only forces on A. Since it's accelerating down, I'm simply going to say M2G, that's 1, minus TA, equals, all right, now I apply the second law, and that's going to be M, and it's the mass of A in this case, because that's what my vectors are on, times the acceleration. Okay, now, I can't really do anything with this because I have two unknowns. I don't know what TA is, and I don't know what A is. So that means I need a second equation, and I can get a second equation by looking at the vectors on force B. So I go over here, and we see that since it's accelerating up, the TB vector is the first one, is the positive one, minus M2G equals M2A. And again, the A's are the same because they're moving as one system. Okay, so we'll come back around to this. So now I have two unknowns. I have A, TA, TB, and A. Now I said two unknowns because we know that TA and TB have to be the same. They're action-reaction. But I'll come back to that when we solve for A. So this is just a little thing, tensions. How does the tension of A compare to the weight of A? How does this compare to this? Oh, I already said this is bigger, but why? And the reason it has to be bigger is because it's accelerating down. If it's accelerating down, the downward force has to be bigger, so TA is less than mg. In fact, we can see it over here that if I solve for TA, I will see, I'll let you rearrange it yourself. I'll actually do it right here. Right? If I solve for TA and move the TA over to here, blah, 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 I get M2, I'm sorry, why did I call it M2? This should be MA. Sorry. MAG. Let me fix that. Maybe. All right. MA, oh, this pen doesn't like this. G minus MAA. Oh, that's really annoying. Okay, so we can see that it's TA equals the weight of it minus MAA. That's just a handy little thing. And then I can do the same thing for the over here. This has got to be bigger than this. By how much? Well, if I look at this equation here, I see TB equals M. I don't know why I kept using the 2's. That's annoying. MBG plus MA. So it's got to be greater by MBA. So the amount of acceleration determines how much we add or subtract from the tensions. Okay, now I already said earlier, let's figure out the acceleration. Since there are two knowns, let's apply the second law for the whole system. Okay, and this is where we want to, and this is what we want to do moving forward. Anytime we want to solve for acceleration, let's apply the second law for the whole system rather than the individuals. When we did this, we did it for the individual. We did it for the individual. There's nothing wrong with that, but like I said, we have two unknowns, so it's hard to move forward. But if we apply the second law for the whole system, then the system being A and B, we take into account all four forces, where this is the biggest force. So I'm going to start there. I'm going to say my sum of all my forces on the system. Okay, so the system is A and B. That's important. Not A by itself, not B by itself, but A and B. So I would say my first force, the biggest one, is MAG. This T is in the opposite direction, so I'm going to minus TA. And this force, even though it's pointing up, is in the opposite direction. They're opposing each other. That's where my tug of war is coming from. So I'm going to say plus TB, because if I'm saying minus TA, I got to do plus TB. And then this is in opposition to this, and that's minus MBG. Okay, so not surprisingly, what we see out of this is these two cancel because they're action-reaction, and since they're acting on the same system, they're internal, they have to cancel out. That's a really important point. They're not external. These two are external because they're coming from the Earth, where these tension forces are coming from within the system of block A and B. So long story short, I'll come down here. I can say for acceleration of the system, then is a net force, which turns out to be MA minus MB. I'm just factoring out the G times G. I just took this minus this. Okay, and then I get divided by the mass. The mass of what? Of the system. And our system is A and B, so it's MA plus MB. And that's actually what goes into here. That's our acceleration for the system. Okay, the derivation might be wonky, but if you want me to cut to the chase as to what you have to be able to do, and if I erase, I got this all messy here, right? It's just do this for the system of A and B. And that's a common theme we'll see throughout. Okay, so if I want to, let's say, I don't know if I had time to set this up, let's say I take a 470 gram mass and a 450 gram mass and hang them here and here. Okay, I want the acceleration of the system. Well, I'll do it down here. That's pretty simple. I would say A is really what this numerator is saying. Remember, we have the numerator and denominator is the net force. And what's really the net force? It's the difference in the weights. Okay, and that makes sense because there's a tug of war between them. The pulley just redirects how they're pulling on each other, and so they're in opposition. So if the weights were the same, there'd be no net force. If one is slightly more massive than the other, therefore weighs more, slightly more, then it's going to be a small net force. So I can just do, and I really don't even have to change the units because they're going to cancel out from numerator and denominator. I can just say 470 minus 450. There's my difference in mass times g. Okay, and then I can divide by the overall mass of the system. And again, I can do 470 plus 450. Because these are grams here and these are grams here, the units will cancel out. So I'm basically left with 20 over 920 times g. And if I want to do, or if I want to factor that, 20 is common to both these. That's 1 over, let's see, this would be 46. So they will accelerate at 1/46 of g. And then I could put in the value of g and get an actual acceleration. We could then predict the time to fall, knowing the distance, but we'll save that for another time. Okay, so this is really important that you understand, to summarize, when you have, in this case, two bodies where gravity is driving everything. Okay, let me erase this and try to make this a little bit more legible to summarize before we end the tutorial. I don't know why that's not erasing. Okay, it's simply this. What we essentially have is, like I said, a tug of war between the weight of that and the weight of that. Those are not the only forces. There are tensions here. Okay, those tensions will cancel out if we treat the system as both the blocks. They will not cancel out if we treat the system as just one block or the other. Okay, so if you're asked to calculate the tension, you just want to apply it to one of the blocks or the other. Don't make the mistake of saying TA equals the weight of A. That's only true if it's not accelerating. If it's accelerating, then there is a plus or minus MA here, depending on which way it's accelerating. Okay, so good luck with the practice. Come in with any questions.